Hello everybody, welcome to the videos for the cumulative review number 14. Let's start here with number 1, which is asking you to find the limit as x approaches infinity or negative infinity. And so as soon as you've seen a limit going towards infinity, this is another way of saying you're really trying to find or think about everything in terms of asymptotes, because asymptotes represent something you're getting close to and not touching, and a limit is also something you're getting close to and not touching. So if we take a look at number 1, as the limit goes to negative infinity, I notice that the beginning powers are even. So what that means is you have a horizontal asymptote going towards y equals the ratio of 6/15. And so that means you're reaching this horizontal asymptote. This could really be reduced if you divide these both by 3 to 2/5. So the limit would be 2/5 as well. Make that a little bit neater. Number 2, as x goes to negative infinity, I notice this time, if we're thinking asymptotes, that we have a top-heavy situation. And when we have a top-heavy situation, that leads to a slant asymptote. So what I'm going to do is find the slant, and then I'm going to use that and draw a picture and think about what my limit has to be. So here, if that's x, let's see, what is that? That's x minus 3, so that means I could do synthetic division, and I could use 3, and then have 6 and negative 8. Bring down the 6, multiply, get 18, combine and get 10, which means if the power is reducing by 1, this is the line y equals 6x plus 10, which as a sketch is a line increasing from left to right. So now if I think about as x is approaching negative infinity, so as x is going this way, my graph is heading downwards. So my limit is either negative infinity or does not exist, based on your interpretation. Number 3 is asking you to find the limit algebraically. And so the first thing we do with algebra is plug in the limit as you're approaching 49. So we'd plug that in for x first to see if we can get a y value out initially. So we would get square root of 49, which is 7 minus 7 over 49 minus 49, which is 0 over 0. And unfortunately, this is indeterminate form, so this does not lead to a limit. So instead, we need to figure out how we're going to manipulate this so that we can find a limit. And the idea of this is using a conjugate. And this question was very much requested to see again on this upcoming test, or at least the review packet. And so if you look at the numerator versus denominator, the piece that causes the problem is the numerator. So what we've done in the past is multiply top and bottom by the square root of x plus 7, or the conjugate. And the key to getting this problem right is remembering that we can FOIL the top, but it would be my suggestion to leave the bottom exactly as you see it, like this. Let me show you. If we FOIL the top and do root x times root x, that is just x. Root x times 7 is plus 7 root x. Negative 7 times root x is minus 7 root x, which makes sense that these would cancel out because they're conjugates. And then negative 7 times positive 7 is negative 49. All over the non-FOILed out bottom, x minus 49 and root x plus 7. So if I cancel these out in the numerator, I would end up with x minus 49 in the numerator, and then in the denominator I'd also have another x minus 49 and a root x plus 7. And so, because these are exactly the same, we can cross that out and reduce this function to be 1 over root x plus 7. And now that this is simplified, now let's try to find the limit again as x goes to 49, which means I could plug 49 in for x and see if I now get a y value. So I have 1 over the square root of 49 plus 7, which is really 1 over 7 plus 7, or 1/14. So the limit, so as you're approaching 49 on a graph, the y value would be 1/14. Number 4, given our graph this rational function, and we need to find all this information first. The reason that horizontal and slant is written first is because they are the easiest to find without any factoring yet. And to decide between these two, we again look at the powers. Because this is top-heavy, that leads to a slant asymptote, which means that I can automatically put that there are no horizontals. However, it does mean that I have to do some kind of division to find my slant asymptote. This time, because the denominator is x squared, I cannot do synthetic division, so I have to do long division. So I'll do that over here. this function into x cubed minus 2x squared minus 24x. So x squared goes into x cubed, or x cubed divided by x squared is just x. Multiply this back through, you get x cubed and then plus 3x squared. However, we need to change the signs on both. And if we do that, this crosses out. Combine down, we get negative 5x squared minus 24x. Is negative 5x squared divisible by x squared? Yes, it is. Negative 5x squared divided by x squared is minus 5. Multiply that back through. We get negative 5x squared. Negative 5 times positive 3x is negative 15x. Change the signs on both of those. These cross out. Combine here, which would be negative 9x. Can negative 9x be divided by x squared? No, it cannot. So for the asymptote, we ignore the remainder, and our asymptote is what is remaining here. So it would be y equals x minus 5. And so far, before I find anything else, let me graph this piece. I know I need it eventually, so I'm going to start at the y-intercept of negative 5, and the slope is up 1 over 1. So I'd go up 1 over 1 all the way up, all the way back. And I know this is going to be here, so I'm going to draw it anyway. Next piece, to find the domain of my function, now is when I would like to factor. So I'm going to do that work down here. In the numerator, I can take out an x, and then if I do that, I'm left with x squared minus 2x minus 24. In the denominator, I can also take out an x, and if I do that, I'm left with x plus 3. I can keep simplifying the numerator. This factors to be x minus 6, x plus 4, all over x times x plus 3. Now, before I cross anything out, I have to find the domain. And so I know from my denominator that x cannot be 0 or negative 3, which means it can be everything else. So my domain would be negative infinity to negative 3, union, negative 3 to 0, union 0 to infinity. The rest of these are all found by my factored version. What I notice is that I can't cross out any of these factors, but I can cross out a single pair of x's, which means that I do have a whole, and when I cross out an x, I get 0, not 1, and I need to figure out the y value that goes with that whole, or the x value in the whole. So what you have to do is plug the 0 in the reduced version, which would be 0 minus 6 times 0 plus 4 over 0 plus 3, which is really negative 6 times 4 over 3, which is negative 24 divided by 3, which is negative 8. So that means on my graph, I have an open circle at 0, negative 8, so I'm going to put that there right now. If I looked at my reduced version here, without the x's, my vertical asymptote is what's remaining in the denominator. So the line I can't cross would be x equals negative 3, and the x-intercepts is what is remaining in the numerator, and this was the denominator. So the two pieces that stay in the numerator are 6, 0, because you have x minus 6, and negative 4, 0, because of the x plus 4. So if I graphed these pieces as well, 6, 0 is right here, negative 4, 0, and the vertical asymptote is at x equals negative 3, right here. So I know my graph has symmetry, and it looks like my graph is working out that way. So we would connect the dots that we have and go along our asymptotes. So my graph would look something like this on one side. On the other side, all I have is 1 point, but I know I'm going to go and remain close to the vertical asymptote and then turn towards the slant. So my picture is going to look something like that. Number 5, solve the inequality by finding critical numbers. This is another one from the last test that I felt could use a little bit more practice. And the first thing we'd like to do is get 0 on one side so that we can compare everything to positives and negatives. So I'm going to subtract over the 2 over 5x minus 2, and that is going to be less than or equal to 0 now. If we would like to combine these two things, we need a common denominator. So this first fraction has the x minus 6, so it needs to be multiplied top and bottom by 5x minus 2. And this piece here needs to be multiplied top and bottom by x minus 6. So if I do that, I would get 3 times 5x minus 2 over 5x minus 6 and x minus 6 minus 2 times x minus 6 over 5x minus 2 and x minus 6. Looking back, this should be 5x minus 2, so I'm going to change that right now. And this is still less than or equal to 0. I'm still trying to find my critical numbers, so I'm going to take these two fractions and combine them into 1. The denominator of both of these is 5x minus 2 and x minus 6, so I'm going to leave those unfactored or unfoiled out. I'm going to leave them in factored form and not going to FOIL them out. The numerator, though, I am going to simplify so I can get a critical number in the denominator. So if I distribute here, I would get 15x minus 6. And be careful, big mistake on the last test, if you're distributing a negative into both, you would get negative 2x and then plus 12, not minus 12. It would be less than or equal to 0. So if I simplify the numerator, I would get 13x plus 6. And on the bottom in factored form, I'd have 5x minus 2, and x minus 6 is less than or equal to 0. Now, again, on the last test, what I noticed was that a lot of students knew that these two numbers down here were critical numbers, but forgot to include the critical number from the numerator. So over here, I'm going to write down the three critical numbers. X equals 2/5. If I set that equal to 0, x equals 6 if I set this piece equal to 0, and if I set 3x plus 6 equal to 0, I will get negative 6/13 for my third critical number. And yes, they are all necessary to find your intervals. And so, if I draw my number line over here, and I put my critical numbers on there, I would have 6, I would have 2/5, and I have negative 6/13. And so I have 4 intervals to check, and the numbers that I will pick for each interval will be the following. I will pick negative 2 for this interval, I will pick 0 for this one, do 1 here, and I'll do 8 here. And I'm going to plug all of these into my most reduced version down here, and we'll think about signs. So, if I plug negative 2 into the top, I'm going to get a negative number on the top, I'm going to get a negative number on the bottom down here, and I'm also going to get a negative number here. Negative divided by positive is a negative, and I want things that are less than or equal to 0, so this interval works. If I plug 0 into this, 0 into the numerator is positive, 0 into the denominator is negative, 0 into this denominator is also negative. So I would have positive over positive, which is a positive answer, which is not less than or equal to 0, so that is not an interval that works. If I plug 1 into this, I get a positive in the numerator. I would get a, let's see, that would be positive here, and 1 into this would be a negative. Positive divided by a negative is a negative, so this interval works because this is less than 0. And I can predict what my answer will be for 8, but let's go through it anyway. Positive into the numerator, positive into the denominator, positive into this denominator, positive divided by positive is positive, which means this is not true. So again, I noticed a few of you on the test did have this correct, but did not actually answer the question in interval notation. So please be careful about that on this upcoming test, if this question is on there. The final answer in interval notation would be this. The two numbers in the denominator are never included, so these two dots must be open because the denominator is never included, but because we have less than or equal to, the numerator always responds or corresponds with the inequality here. So this would be a closed dot, which means that my interval notation would be negative infinity to negative 6/13 with a bracket, union, this piece, which both be parentheses, union 2/5 to 6. Just making this a little bit neater, but this is the last problem I will be doing in this video. This problem took a little bit, and we'll continue on the next one. Thanks, everyone.